Okay. So, to access online MATLAB, you have to go to matlab.mathworks.com. You need to have a license in order to access this. IIT Madras students do get a license, at least for this course you will be getting. I think in general, as long as you are IIT Madras students, you do have a license, but you will have to use your SMail IDs in order to log in. Okay. So, do not use your Gmail or any other email ID, you have to use your SMail ID, so that MathWorks recognizes you as a legitimate IIT Madras student. So, you will be able to access online MATLAB. If you have desktop MATLAB access, or if you are going to use that use MATLAB in your DCF, feel free to use the desktop version. Okay. For this course and for most of the things, there is no major difference between functionalities of online MATLAB and desktop. Some minor, one or two minor differences might be there, but you know, they shouldn't matter too much, at least. Okay. So, I am going to demo things on the online version itself, because we do not have MATLAB on this computer. Okay. So, MATLAB stands for, it does not stand for, the name originated from MAT stands for matrix, LAB stands for laboratory. So, the idea at that time was that this was in late 1970s, was rather than students writing codes in Fortran, give them a particular mechanism where they can directly start using this in linear algebra and controls courses. Okay, and that is the origin of MATLAB. Okay, so, MATLAB did originate with a matrix based thinking. Okay. So, everything that MATLAB does, it does matrices very naturally. Okay. So, that is the one of the main features of MATLAB, and the professor who came up with some of the concepts and the founder, or Jack Little, who is the founder of MathWorks, both of them were a little bit from controls background, if you can, or systems and controls background, and that is partially also the reason why it became very popular in control community right since its initial days. Okay. So, MATLAB has scalars and has vectors. You can assign a value to any scalar. So, if I say a equal to 1, that is an assignment operation, and a gets the value of 1. If I end the line with a semicolon, the value does not get displayed. Okay. Just as the previous code here, b equal to 2 also got executed, you now have the vector a having value of, let me just clear everything. Clear all will basically clear all the variables in its memory, and CLC will clean the screen. Okay. So, a equal to 1 without a semicolon, it will display, b equal to 2 with a semicolon, it will not display. Okay. You can do any type of operation, say multiplication and so on, and this, if you want, say, to get sine, you can get sine of a. Okay. A over here is in radians, sine would be in radians. If you want to get sine inverse, it is a sine. Yeah. Right. So, this is what you expect, right. So, sine of a is pi by 2, I have just multiplied it to show you that it is pi. Okay. A and s is a special variable. If you execute a command, but do not assign it to a variable, that value gets captured in a variable called a and s. Okay. Some of the other special variables are pi. Okay. If you type I, then that is the complex identity. Okay. But if I say I equal to 5, okay. So, from now on I will not be complex identity, but I will have a value of 5. Okay. So, if I type I, see I has the value 5. Okay. These are scalars. If you want to give vectors, you can give a row vector in this way, separated by spaces, okay, or separated by comma. If you want to give column vectors, it needs to be separated by semicolon. Okay. Transpose is the apostrophe that is next to your enter button, that is transpose. Okay. Remember what we did last week? A into A, you get an error, not commutative under multiplication. A into A dash, exactly what you guys had said the other day. A dash into A, also exactly what you had said the other day. Okay. If you want to give a matrix, okay. Oh, I meant to type a semicolon, but I forgot to. But let's press an enter and see what happens. You will get an error. Okay. Why you are getting an error? The first row has 6 elements. The second row has only 3 elements. Okay. MATLAB has no way of knowing where you have made an error or to guess where you have made an error. So it is going to just throw that error. This is what I wanted to do. Okay. So first row is 214, second row is 310, third row is 113. Okay. Now if you wanted to find eigenvalues and eigenvectors, the command is EIG. Okay. So if you give EIG of A, you will get the eigenvalues. Okay. We had said that eigenvalues need not be real, they can come in complex conjugate pair. Yeah. So we had said that eigenvalues need not always be real, they can come in complex conjugate pair, which is what you see over here. This and this forms a complex conjugate pair. Okay, let's give another A, 1 4 1 2 0 3 1 1 2. Let's see. I want to give an A which has real eigenvalues. Okay, good. Okay, so this A, all the 3 eigenvalues are real, all the 3 eigenvalues are distinct. Okay. EIG is also the command that you will use to get the eigenvectors. Okay. The way to get that is again with EIG, but I will explain this in a bit. Okay. This is the first eigenvalue, this is the second eigenvalue, this is the third eigenvalue. This guy over here is the first eigenvector, this is the second eigenvector, this is the third eigenvector. Okay. So the columns of the V matrix are eigenvectors, the diagonals of the L matrix are eigenvalues. Okay. The other thing that you will notice is that if eigenvalues are distinct, then eigenvectors would be unique. Okay. If you have distinct eigenvalues, you will have unique eigenvectors. And not just that, it is interesting that they are going to be linearly independent and therefore they can span the entire 3-dimensional space in this case. Okay. That is a very important result. We will come to what is known as eigenvector decomposition, okay, but let me demonstrate that to you. Okay, sorry, let me demonstrate it. Let's do it this way. Let's get the eigenvalues of A. Okay, let's create a matrix lam equal to ANS 1 0 0 0 ANS 2 0 0 0 ANS 3. Okay. So, what I am doing is I am creating a matrix such that 1 1 value is the first eigenvalue, 2 2 value is the second eigenvalue, 3 3 value is the third eigenvalue. Okay, which is of course same as the matrix L, but this is the matrix that I have created. Okay. Another way to create this is, let us say ANS, yeah, lam equal to dag okay. So, if the argument of diag is a function in MATLAB, if an argument of diag is a vector, it will form a matrix. If it is an n dimensional vector, it will form an n by n matrix such that the diagonal elements of that n by n matrix will be the elements of that vector, non diagonal elements will be 0. Okay. So, diag acting on a matrix, sorry, on a vector will create a diagonal matrix, diag acting on a matrix will extract the diagonal elements. Okay. So, if I do diag A, it is extracting the diagonal elements 1 0 2. Okay. That is what diag does. Let us go back and look at the EIG command again. Oops. Okay. This was the EIG command. This is how you will write all your functions. EIG is the name of the function. Immediately followed by name of the function in round brackets will be list of input arguments to that function. Okay. Before the equal sign, inside square bracket there is a list of output arguments. Okay. Do not, so sometimes new students do this. Okay. Okay, not right. The syntax is that inputs have to be inside round brackets, okay, and the outputs have to be inside square brackets. So, this also will be incorrect, invalid expression. Okay. Okay. So, let us say this was our A matrix, we had created our lam vector and we have the matrix of eigenvalues, eigenvectors. Okay. I and V is inverse. Okay. So, let us look at what V lambda V inverse gives us. Okay. Let us compare that with A. Okay. Because this is real number operation, that is why you are seeing 0.000, 1 2 1, 1 2 1, 4 0 1, 4 0 1, 1 3 2, 1 3 2. Okay. This is an important result which I am going to talk about in a bit. This is what is known as eigenvalue decomposition, also known as vector diagonalization. Okay. Let us also do this. So, V1 is V, okay, let me show you that. V1 is capital V, colon stands for all or colon stands for 2. Okay. If you say 1 colon 4, it is 1 to 4. So, 1, 2, 3, 4. If you just put colon, everything from start to end. If you want to do 1 to 4 in steps of 2, it is 1 colon 2 colon 4. So, that will become 1 and 3. If you do 1 colon 0.5 colon 4, it is 1, 1.5, 2, 2.5, 3, 3.5, 4. Okay. So, this is the first eigenvector . Okay. So, V1, V2, V3 are the 3 eigenvectors. Okay. Eigenvalues we will say L1 okay. So, this is L1, this is L2, this is L3. Okay. So, we have designated those 3 as the 3 eigenvalues. Okay. Let us actually say that you know what MATLAB has designated those as lambda 1, lambda 2, lambda 3, but let us say when I solved and I got the 3 eigenvalues, let us say I called L1 as the first eigenvalue, this L3 I thought was the second eigenvalue, and let us say L2 I got as the third eigenvalue. So, let me make lam equal to L1, L3, L2. Okay. So, what is the ordered eigenvectors? V1, V3, V2, because V1 belongs to L1, V3 belongs to L3, V2 belongs to L2. So, we will make matrix V1, I will call this as capital V new, as V1, V3, V2. Okay. Keep in mind L1 corresponds to V1, L3 corresponds to V3, L2 corresponds to V2. What I mean by that is, in the lambda matrix I have 3 eigenvalues, in the V matrix I have the corresponding 3 eigenvectors. Okay. Even then this diagonalization holds. V new into lam into INV V new. Okay. 121 401 132. Any questions so far? Okay. Finally, singular value decomposition U comma S comma V equal to SVD A. Okay. Okay. This is the first singular value, this is the second singular value, this is the this is the first input vector, this is the second input vector, this is the third input vector, this is the first output vector, second output vector, third output vector. sorry, I made it ulta. V is the inputs, U is the outputs. So, this is the first output vector, second output vector, third output vector, and this is the first input vector, second input vector, third input vector, and these are the 3 singular values. Okay. You will always get it in this particular format. The U matrix and V matrix are going to be orthogonal matrices. S will always be such that its diagonal elements are positive or 0, its off diagonal elements are always 0. Okay. So, let us say if we had B equal to 1, 2, 3, 4, 5, 6. Okay. If we did a USV on B, SVD on B, okay, what we should get? We should get U as a 2 by 2 matrix, S as a 2 by 3 matrix, V as a 3 by 3 matrix. Okay. S1 and S2 may either be positive or 0, remaining everything is going to be 0. Yeah, this is what you get. Okay. The other interesting thing is that this guy, this vector that is associated with 0 or no singular value, that is the null, or that is the vector in the null space, or it spans the null space. Okay. And the vectors of U that correspond to non-zero singular values, they span the image space. Okay. Because the rank of the B matrix was 2, therefore, the image space is 2-dimensional space, the null space is 1-dimensional space. Okay. So, the image space is going to be equal to rank of A. The null space is going to be equal to number of columns minus rank of A. Okay. Let us look at the case where we had our A equal to 1, 2, 0, 0, that we talked about in yesterday's class, right. So, let us do the SVD for A. Okay. What do we expect to get? Let us talk about singular values. What do we expect as singular values? Do you expect S1 to be positive, 0, negative? Positive. S2 to be positive, 0, negative? 0. Why? Because that is the rank of the matrix. Rank of the matrix, if you remember from yesterday's class, rank was 1. So, number of positive singular values will exactly be equal to the rank of the matrix, rest will be 0. They might show up exactly as 0, or they might show up as an extremely small value because of truncation errors, or because we are working with real numbers, but they are 0 for all practical purposes. Okay. What do you expect with respect to U then? Yes. Now, U we said is the columns of U that are associated with the image space will be the first guy, right, and the columns of V that are associated with the null space will be the second guy, right. So, let us see what we get. Okay. S, as you can see, this guy is 0, yes, because rank of the matrix was 1. So, only one singular value is non-zero. Okay. what was the image space? The image space was the height, it is the x axis. So, the first u vector is going to be 1 0, right. What does 1 0 mean? 1 0 means the x axis. Okay. What did we say was the null space? Minus 2 1, we actually said 2 minus 1, but yeah, this one is showing the null space as minus 2 1, right. How do you check that it is minus 2, it is equal to minus 2 1? It is going to be minus 2 1 would be negative of 4, sorry, negative of 2 divided by square root 1 square plus 2 square. Right. So, this is minus 2 1. Remember in one of the classes we did change of basis. This is the reason why this works this way. V becomes change of basis for the input space. So, if you multiply input with V inverse, we are going to get the output which is diagonalized. Okay. So, this is the singular values, singular vectors, V singular vectors. So, V transpose multiplied by U, your input, is going to be input along the null space and the perpendicular line to the null space. That you are going to multiply with S. Okay. The thing that is not along the null space will get multiplied by the singular value S1. The thing that is along the null space will get multiplied by 0. So, the thing that is along the null space will be projected onto 0 when you take the image. The thing along this line we will get the output, but that output will not be under the natural basis, that will be under the U basis. In this particular example, U basis happens to be same as natural basis. Okay. That is how this works. Okay. Shall we move on? There was one question actually yesterday after the class. What is the purpose of SVD? I mean, is SVD going to be important for this course? Yes, SVD is quite important for this course. Now, where is the practical implication? What we saw in yesterday's class, one of the practical implication was that if you, for example, if you choose the two inputs, two inlet streams, sorry, if you choose the two inlet streams to have the same purity of mixture, so 60% mixture, both inlet streams is there, there is absolutely every way you can change the height, but there is absolutely no way you will be able to change X, the purity, right. That is one thing. Again, because it was a 2 by 2 system, it was obvious. The other thing that we saw is if you ended up choosing XA and XB, the purity of species A and purity of species B as your two manipulated, as your two controlled variables, there is no way for you to independently control them. Okay. If someone says that I want XA to be 0.5 but XB to be 0.3, it is impossible. Why? Because XA plus XB is going to be equal to 1. Again, this particular thing was obvious. It was obvious because we kind of concocted that example that way. Okay. Now, let us talk about the example that I showed you in the first, in the introductory MPC class. In the introductory MPC class, you saw an example that had 25 inputs and 40 outputs, right, which basically means that not all 40 outputs can be controlled any which way that you want. Remember what we said, that the number of the row rank is equal to column rank, right. So, In this particular case there is 25 inputs and there are 40 outputs, that means it is 40 by 25 matrix, the A matrix. Out of these 40, only in at most 25 directions can you control the system. Does not mean only 25 variables can be controlled, in only 25 directions. Which directions? Given by u1, u2, u3 and so on, which correspond to the positive singular values. Okay. So now if for example someone tells you that these 40 variables I want to control at these values, all you need to do is to find out whether those 40 values that somebody asking you to give, is that lying in the span of those 25 vectors. If they lie in the span of those 25 vectors, yes, you will be able to control. If they do not lie in the span of those 25 vectors, no, you won't. If you did not have this SVD fundas with you, you will never be able to analyze that. Okay, and we see this all the time. Problem is formulated that A has to be at the set point, B has to be at the set point, C has to be at the set point, D has to be at the set point, and it is not achievable simultaneously. Okay, then you realize, well, actually if you do SVD it was not achievable at all, because in this way, because you have only 3 inputs. Okay, and because there was a full column rank, so you could so the column rank was full rank, so the row rank was also 3. So at most in 3 directions you could control this, which basically meant that if you fixed A, B and C, your D gets automatically fixed. So then you just reformulate, let us say D was temperature. Okay, temperature you had earlier said I wanted to be controlled at 450, but after seeing this you realize after fixing A, B and C, your temperature gets controlled at say 445. You say, you know what, I am happy with it, let me change the control requirement. I change that control requirement, I am fine. This is where, and this is, this is an obvious example, you will see more examples later on where something like SVD is useful. Okay. So we had said that any vector A can be written as x lambda, or sorry, not x, v lambda v inverse, right. This kind of a transform, or we can write this as lambda is v inverse a v. Okay. This transformation is called a similarity transformation. Okay. If you obtain any matrix B as P inverse AP, then the matrices A and B are said to be similar. Okay. Very interesting properties of similar matrices. This can all be proved, you do not have an assignment to prove this, but yeah, you can prove that two similar matrices have the same eigenvalues. Okay. Of course, because they also have the same eigenvalues, their rank will be the same. Very important result, B to the power n is P inverse A to the power n P. Actually very easy to prove, right. B equal to P inverse A P, okay, you multiplied by B, which is P inverse A P multiplied by P inverse A P, right, and this also exponent. Okay. Again, this is also quite interesting. Why is this interesting? Is because you remember how we write Maclaurin series e to the power x, it is EU. Likewise, you can write e to the power a as 1 plus, sorry, I plus a square by 2 plus a cube by 3 factorial plus so on. Okay. See this result? So, each of these guys satisfies this result. You take p outside, put everything else in the bracket, you have e to the power b. So, that is how, that is one way to prove it. Okay. And this is an extremely important result. Why is this extremely important? This is one of the ways in which you can compute exponent of a matrix. Remember where we talked about exponent of the matrix? If you have dx bar by dt equal to ax, where x bar initially equal to x bar naught, you had e to the power at. This is where this funda will be useful. Yeah. So, the diagonal canonical form that we talked about, right, is A equal to V lambda V inverse, okay, which is V1 bar, V2 bar and so on up to Vn bar multiplied by lambda 1, lambda 2, okay. This is another notation I would want you to start being comfortable with. Okay. Right. If you see V1, if you see V2, right, V1 transpose, V2 transpose is going to be, which is exactly what this is. Okay. So, if you were to transpose this guy, let us say if this was scalars, if V1, V2, V3, V4 were scalars and you had a row vector, if you were to transpose that, it will be V1, V2, V3, V4. Almost in the same way transpose of a matrix works. It will not be V1, V2, V3, V4 because V1 would be n dimensional, V2 will be n dimensional, V3 will be n dimensional. So, if you wrote as V1, V2, V3, V4, it will mean n square dimensional long matrix. That is not what that matrix of transpose is, right. So, it is V1 transpose, V2 transpose, V3 transpose, V4 transpose. Okay. Something that we are going to use quite a bit in rest of the course. So, please get familiar and comfortable with this also. Okay. Writing A in this manner is expressing A in a diagonal canonical form. Okay. Unfortunately or fortunately, it is not all that unfortunate. So, sometimes what happens is you have repeated eigenvalues. Okay. Let us say 1 to 0, not 0, right, 1 to 1 something x. If you want to get this eigenvalues, what we will have 1 minus lambda x minus lambda minus 2 equal to 0 lambda square minus 1 plus x lambda plus x minus 2, no. How will you complete squares? If x is 1, right, if x is 1, yeah, I can make this 2 minus 2, no? This will have repeated eigenvalues 1 minus 2 1 1, no. Oops. Oh no, it is not repeated, sorry, some mistake. Okay, forget it, let us erase that and let us. let us say you have a 2 by 2 matrix A, and let us say its two eigenvalues are lambda, okay. Then you will not, so often you will not be able to get two eigenvectors, you will get only one eigenvector V1 and you will get a generalized eigenvector, okay. So what is a generalized eigenvector? Eigenvector is A minus lambda I V bar equal to 0 bar, okay, and generalized eigenvector is W bar such that A minus lambda I W bar is not equal to 0, but A minus lambda I squared W bar equal to 0. This is the definition of generalized eigenvector. I do not want you to really use it to get anything, okay. You will use EIG command in MATLAB to do all of this, okay. But if there are repeated eigenvalues, okay, then A will be represented as V lambda V inverse, where V is going to be equal to eigenvalue and generalized eigenvalue, okay, and lambda, this is important, is going to be equal to lambda 1 0 lambda, okay. See the difference? The difference, if okay, then V capital V was equal to V1 bar V2 bar, okay. But if lambda then this is the structure, the lambda in that case was equal to lambda 1 lambda 2 0 0, lambda in this case has 1 in the non-diagonal element. If lambdas are repeated 3 times, then the Jordan canonical form is going to be lambda 1 0 0 lambda 1 0 0 lambda. If let us say there are 4 eigenvalues and they are lambda 1 lambda 1 lambda 1 lambda 2, then this will look like this. Okay. Let us say there are 4 eigenvalues which are lambda 1 lambda 1 lambda 2 lambda 2, this will look like lambda 1 lambda 1 lambda 2 lambda 2, okay. This is 0 0 0 0 0 0, be 1 over here, there will be 1 over here 0 0 0 0, okay. You see this structure, this is same as this structure, okay. That is the beauty of it, okay. Put those, instead of having those lambda lambda in the vectors, now you have those as block diagonals, okay. That's, I mean it's that's one of the things that's really nice about linear algebra. Don't get too carried away by that, I mean that you can make mistakes over there also, but check, verify when you are learning and you should be fine, okay. I will skip the square canonical form, okay. So remember the Jordan canonical form and similarity transform. So if B and A are similar, then this is the value, okay. A is V inverse lambda V, right. Lambda was V A V inverse, sorry, right. So we can write A as V inverse lambda V, okay. So e to the power A is V inverse e to the power lambda V. The beauty of this is exponent of is equal to e to the power lambda 1, e to the power lambda 2, 0, 0. Okay. So, if you want to find e to the power a, that is, so get the eigenvector decomposition, what about the Jordan canonical form? Okay. Again, a is V inverse lambda v. So, e to the power a is V inverse e to the power lambda v. Okay. Okay. Yeah, diagonal, you have this as e to the power 1, this as e to the power 1, this is 1 1. Oh, sorry, yeah, 1 expm. Sorry, my mistake. exp will do element by element exponential, expm does a matrix exponential. E to the power lambda 0 0 e to the power lambda. Okay. Oh, oops, this was our L, right. So, L first row second column element is equal to 1. Okay, actually, okay, that is fine. expm of L, you will get this. Okay, it's probably a bad example. So, let us make L equal to say 2 1 0 2. That is probably a better example, right. So, exp2 is 7.38. So, we are expecting 7.38, 7.380, 7.38, right. So, let us do expm. Yeah, element by element exponent. Right. So, this is e to the power 2, e to the power 1, e to the power 0, e to the power 2. Okay. I think that is pretty much what I have. One more thing is, so you had e to the power at, right. So, how do you calculate e to the power at? If this was what it was, okay, it will be this one. Okay. Fun, no? We will try that out. Let us say t was 0.1. Okay. So, exp L into 0.1. Okay. So, e to the power 0.2, e to the power 0.2 and 0.1 multiplied by e to the power 0.2, that is what you are supposed to get. Sorry, expm. sorry about that again. Yeah, e to the power 0.2 is 1.22, e to the power lambda t, e to the power lambda t, t e to the power lambda t, 0.1 multiplied by that, and this guy is 0. Okay. You may not need to hand calculate things in this course probably, especially if you have access to MATLAB and you start using MATLAB. But it's always good to know how to hand calculate, because if you make a coding error, you can check them. Okay, you will be writing a fair number of codes, so knowing this fundas will. So you saw how many times I did this mistake of using EXP instead of EXPM. And I have been coding in MATLAB since 1999, right? So in 20 years, I am still sometimes making this mistake. And how do I know? How do I immediately know that I have made that mistake? I see that 1 over there. I know that that can't be 1, and and that's how probably some of you also pointed out that error. Okay.